Alright, hey, what's going on, guys? Today we're going to be talking about quantized energy within our quantum fields. So let's go ahead and get started. Make sure to hit that like and subscribe button. Make sure to go onto my Patreon page if you want to contribute to the channel there. You can also become a member here as well on YouTube. So let's go ahead and get started. So we're now going to aim to extract some physical intuition about our Klein-Gordon field. Recalling what we did last time, we discovered these commutation relationships between these are the coefficients, right, on our plane wave solutions, or on our wave solutions for our general solution of our Klein-Gordon equation, right? So our general solution, again, looked a little something like, reduce the thickness on my pen here, it looked a little something like phi of x and t, and it was a sum of waves, right? K mu x nu. This isn't exactly how it was written out last time. It was a little bit more fleshed out, but this k mu x mu, these are four vectors, right? Where k mu encompasses the frequency in the temporal dimension, and then in the frequency in the x direction, frequency in the y direction, and frequency in the z direction. We can actually write this as we have k x, k y, and k z, right? And this is equal to our k mu, which is this guy up here. Then we had these coefficients, and these coefficients were functions of our k values, right? So these k values, these are the frequencies, and which are right here, and then these coefficients are functions of those frequencies, right? So if you have some wave, for example, that has a certain frequency, whatever frequency this thing has, the frequency is related to the wavelength, so that's going to be, so whatever frequency that this is, say this is k1, well then we attach a number to that k1, and that's going to be a, right? So we have these waves, they're solutions to our Schrodinger equation, and these waves, when they add up with each other, they add up to create some complex looking wave. And each one of these, so we'll have a wave that looks like this, and that plus a wave that looks like this, right? So, and each one of these has their own unique frequency to them, and then each one of those gets a coefficient attached to them, right? So that was the general solution. We saw then that these guys here, these coefficients had a commutation relationship to them, which looked like this, and then these two guys as well, where we allowed the coefficients to take on complex values, and so this dagger here means that it's the complex conjugate of this one. Alright, so these are commutation relationships. They came about, again, by imposing the Heisenberg uncertainty principle between our fuzzy positions and the canonical momenta for these positions. In a mathematical sense, these commutation relationships are the quantum field theory version of the uncertainty principle. So we went over this, but let's go over it a little bit again. So in quantum mechanics, we have our canonical position variables, we have our canonical momentum variables, okay? We then applied Heisenberg's uncertainty principle, and when we did that, essentially what that was we had our positions, they were a function of x and t, and then we had our canonical momenta, they were a function of x and t then, and we found the commutation relation. We said that the commutation relationship between these two things was some value, right? This commutation relationship was related to the commutation relationship in quantum mechanics, right? So it was a little bit more complex, but we had this IH bar, and then we had some delta function out here as well. But by doing this, right, we then came to this, right? So if essentially what we're saying here, is that if there's a canonical if there is a commutation relationship that we could find for these two guys, we should be able to find commutation relationships then for our coefficients for these plane waves, okay? And so this is the general workflow. What I'm gonna decide to do here is we're gonna add on to this workflow as we continue with this series, okay? So let's keep a mind on that, okay? So in the last video, we also established these guys right here, right? So this is our solution. It's a sum of waves of different frequencies, right? So the sum is given to us by the integral of waves is given to us by this and by this d3k. So these are three-dimensional waves, and then this normalization factor is useful as well, which we found out why we had that in the last video also. And then we have and then these are our waves, okay? Same thing for our canonical momenta. That was just the temporal derivative of this thing, right? So that's where we get this drop down of this negative I omega. And then we can also do the spatial derivative, not just the temporal, and we get this guy as well. We're going to take all of these then and we're going to plug them into our Hamiltonian. Our Hamiltonian is given to us by the T00. This is the 0,0 component of our stress energy momentum tensor, and the 0,0 component is the energy portion. So we're saying the total energy. The total energy is what we're going to call our Hamiltonian, and this thing we said was a symmetry of our Lagrangian, and that was specifically a space-time symmetry of our Lagrangian, which was given to us by this equation, which we calculated also. Okay, and then we also found this thing out then. So from here we got this. So now we're just really going to plug these in to here, right? Because we have this thing here, which is right here. We have this thing here, which is right here, and we have this thing here, which is right here. All right, so let's go ahead and do that. There's going to be a lot of math involved here. I wouldn't get too scared of this because I try to color code a lot of stuff and try to make this as compact and as succinct as possible. Again, the aim here that we want to get to is our Hamiltonian in terms of these coefficients, okay? Because we want to understand what the physical nature of these coefficients is, okay? Okay, what's to follow is a lot of math. We're going to start off by plugging 4, 5, and 6 into 7. So here's 4, 5, and 6. So that's these guys into this guy right here. And when we do that, we get all of this, okay? And so we can see that, right? So this thing here is right here. And then we're going to square that. So we need 2 of them, right? So square them. We need 2 of these guys, which is right here. So we're going to get these guys, and we have to square these as well. And we're doing this over two frequencies, right? A K and a K prime frequency. And then this right here. When K prime is equal to K, then these are just going to be squared, right? But we're doing this over 2 frequencies, and then we'll use a direct delta to collapse them. So right now, this is the most general way of writing this, because we're saying that these two things are different. But then later we're going to say we're going to collapse this prime to be no longer a prime, and then everything's gonna collapse down. So here is our Hamiltonian then. Our Hamiltonian. So from here to here, there really isn't a lot to this, right? So we have this guy here, which is here, this guy here, which is here, and then this m squared times all of this, which is right here. These guys, right? So we have a e to the ikx. There should be no cosine there, right? That's a misprint. So this should be an e. That's an e. So we have e, and this e here is going to be right here, right? So, and then we also have it right here, and so I'll just highlight these. So here's this guy, and this guy, and then this guy, this guy, and this guy, and then actually we have primes, right? So we have primes, and so our primes, I'll just do it in the same color right here. Primes, everything with the minus k, right? And then this guy, and then this guy, and this guy right here. All right. Okay, so now we're going to defer to Fourier analysis to draw the following equalities here. So these equalities come from Fourier analysis. If you're not aware of how Fourier analysis works, really what this is if you have some wave, I'll do that. If you have some wave, suppose it looks like this. This wave has one frequency. Okay, this wave has one frequency. That frequency is related to, not h. Oh my gosh, this pen is very finicky. This is some frequency related to the wavelength, and we can convert this thing into a spike in frequency space. So if this is position space, this is frequency space, this spike is going to correspond to the value of this frequency right here. Okay, so a wave of one frequency is going to correspond to a spike in frequency space. Now, when you do this when you have a wave that looks like, when you have a wave that looks more like this, say, we have now this thing is equal to this wave plus this wave, say, I'm not really specifying anything too technical here, but the idea here is that if you have some complex looking wave, well, that's the sum of simpler waves. And these simpler waves, again, they have frequencies. This one has a much higher frequency, and they can get converted then into frequency space, where we have a frequency here, and then this one, say, has a higher frequency, which is out here somewhere. So for this guy, we have in frequency space something that, say, looks like this, where the height of these things corresponds to the degree, how much of the wave is getting added. Okay, and how much of that wave is getting added corresponds to these coefficients, and we'll come to that. But that's Fourier analysis in a nutshell. What we can do now is we could see that if we have some wave, e to the I k minus k prime, we could split that up into its the k minus k prime. There's a little bit of ambiguity here, because when there's no arrows, we're supposing that this is these are four vectors. We can split them up into the temporal portion, and where we have the minus sign on the temporal portion due to special relativity, and then this portion here, which is the spatial portion, and that is all equal to this right here. So we have this bit out here, which is right here. Because we're integrating over x, this is the only part that's getting integrated over. And so what this is a spike, right? This here is a spike at the value of k minus k prime. That spike, again, is these spikes, is one of these spikes right here. So we're taking this complex wave, okay? We're taking the spatial components of this complex wave, and we're saying that this thing corresponds to some spike in frequency space, okay? And that spike is given to us by this direct delta. When this is equal to this, we get direct delta of 0, and the integral under that direct delta is going to take us to infinity. So that's how we write this. We write this as a direct delta function, okay? Then we have this normalization factor out here, and this is one of the reasons why we have these normalization factors down here. We'll see how this works, but that is that, right? That the idea again is we have this guy right here, and then this can get collapsed into this right here if we were to consider them as 4 vectors, okay? And we can do the same, actually, no, so this thing, if omega prime is equal to this is going to go to 0, which is why we have a 1 right here. Because we're going to ultimately collapse omega prime to omega. And so when those things are equal, we get e to the 0 power, which is 1. Same thing here, right? So when we stare at this thing, we look here, this is going to be 2 omega, because it's omega plus omega when we do this collapsing. And so what we get then is this 2, this factor of 2 here, okay? And then everything else stays the same. If you're not familiar with Fourier analysis, just take these as identities for right now. And I'm thinking about doing a series on Fourier analysis as well. It's a whole field in and of itself, which is super interesting. So for right now, we could just take these as identities, okay? We're not really in this to learn Fourier analysis. We're in this to learn quantum field theory. Anyways, if we take these as identities, our Hamiltonian is going to get really ugly, but then it's going to get really pretty, okay? There's always a storm before the rainbow, right? In anything in physics, there's always a storm before the rainbow. I remember when we went through the Weyl tensor some months ago, that got really ugly, but then it reduced down to something really nice. So that's a general principle everywhere. Things get ugly before they get pretty. Anyways, this is what this is going to turn into, right? We have this really ugly beast of an equation then for our Hamiltonian, because we're plugging these guys, these identities, into these guys, right? Because we have this e to the I kx, right? And that's, we have it here, we have it here, we have it here, and here, everywhere, right? So we're plugging these things in, okay, and we get all of this stuff, right? So let's just take a look at one of them, and we'll see how this works. So here we have our 2 pi cubed. Here's our 2 pi cubed. Here is this guy right here, which is right here, and then this guy right here, which is right here. We integrated over e to the minus I k plus k prime x, okay? So that is e to the minus I kx. So wherever we see this minus I, we're literally just plugging in this identity right here. Okay. All right. And we have this a times a, this ak times ak prime. Right, so, and this thing comes from, I'm color coding a bunch of stuff here, but this thing comes from doing our commutation, right? So this thing times this thing, and then this thing, or times this thing, or this is all just multiplication, not commutation, right? So we're multiplying these things out, then we have this e to the minus ikx, all this stuff, and we get this right here. All right. Okay, so let's continue now. Our Hamiltonian is now going to be this thing, thanks to all the color coding, right? So the color coding here, so we have the red bit goes out here. These are all just numbers. Okay, and then these guys, well, we can bring them out here, right? Again, because this is just a Kronecker delta, we could treat it as like a constant, okay? And they're all the same. We're not really treating it as a constant. It's still inside the integrand, but all of these have the same, all the same Kronecker delta, so we could just pull them out. Then we have omega minus k, omega minus this, minus the m, or plus the m squared, because we have that m squared out here. All right. The reason we are able to pull this m squared out is because everything is going to, so we have this guy here and this guy here, which is right here. This guy here and this guy here, which is right here. And then we have this guy here. And so this is AK prime, right? So AK prime, okay. And then we have A dagger. So if you stare at this long enough, you could see how this is all going to collapse to this right here. This is a commutation, or not a commutation relationship, right? This is just this times this times this, okay? And you can see, right, I don't want to dwell too much on this because I'm already 20 minutes into this and we still have some stuff to go through. And so actually, with that being said, you could stare at this and you can see how this works, okay? And then we have this constant of 1/2. So to get from the first equation to the next, we recall 2 and 3. So I sort of stepped through this already, but again, 2 and 3. We want to recall these guys here, and those two guys are going to help us reduce some this guy and this guy to 0, this guy and this guy to 0. All right. To see that the terms with the two non-dagger and the two with the dagger terms will commute to 0, and we can now integrate over k prime. So when we integrate over k prime, then we're collapsing this Kronecker delta, or this Dirac delta, is going to collapse all k primes to k. So everything that has a k prime is going to get reduced to k, and so we get this from here to here. Then we use this relationship, right? Because we have this plus this, right? But this is the square of the square root of this, right? So we're going to have two of them, right? So we have this thing then, and then from here to here, we just use equation 1, right? Equation 1 is this guy up here, okay, to get here. Okay, you may have to stare at this a little bit because this here, this is just if you take two of these guys, this might be a good exercise actually. If you could take this thing. So we have that the commutation is A dagger plus A dagger A, or minus, right? That's the commutation relationship. So, not equals. This is going to be minus, right? So that is equal to that. And so what we have is A dagger is equal to A dagger minus A dagger A. And when we look down here, we have A dagger A, right? That is this right here, okay? So that means that that's equal to this, which is equal to this up here, right? So which is where we get this right here. Our Kronecker delta then is 0 because we collapsed the k and k primes. Oops, the k primes to k, and so that's where we get this 0 from. So I'll just erase my messy handwriting, and we get to here now. Because this thing is infinitely large, so we're going to ignore this term. Okay? All right. So this 2 is going to cancel out with the 2, and we get this. Okay, so the Hamiltonian is now rewritten not in terms of total energy, but now our field, not in terms of the total energy of our field, but now the coefficients on the plane wave solutions. So we still don't really have an intuitive grasp on what these coefficients do physically for our fuzzy spacetime points. So let's apply this to an arbitrary energy state to see what it does. when we see what it does to an energy state, then we can get a physical intuition for what it is. So we have so we're going to ignore the n for a second here. We have h, we're going to apply it to A and then to an arbitrary energy state. So here's that A, this one right here, right? So this guy here is this guy right here. This right here is our Hamiltonian. And so to get from here to here then, right, we have, excuse me, I can move this guy over and we get this. So we're literally just swapping these two guys. All right. My apologies for the dog barking. And so then we get this guy right here, right? Because then this here we can write, this is A dagger A. And then, so if we write this commutation out and then we do this subtraction, what we actually get is this guy back from, when we do this subtraction from of this to this, right? Because this is A dagger minus A dagger A, and that's going to be, we're going to subtract that from A dagger, right? So, and what we get is, these two guys are going to cancel, and we get the A dagger A, which is A dagger A right there. And so we get this right here for our Hamiltonian. Continuing, we can then get this, right? Because this was our commutation relationship. Our 2's are going to cancel. We're going to cancel out. Well, so actually what's going on here is this now, this here is going to be applied to over here, and it's going to be applied to over here. Right? So when it's applied to over here, we get this because the 2's and these guys will cancel out. And then we get all of this out here, which is when we brought it over here. Okay? So we get this then, from here to here then. Well, this is just our Hamiltonian, right? So that's our Hamiltonian times this. Then we have all this out here. And then from here to here, our Hamiltonian is just our total energy. And so we get this. And so we can then factor out we can factor these guys out, we can factor these guys out, and that's these right here. And so we get E minus omega right here. And so now we can see the physical relevance of this Hamiltonian. Given that these are coefficients, again, on the plane wave solutions, we can write from equation 25 that we have now this, right? So now we're fleshing everything out, because remember, the ends now become relevant. The ends specify which wave these coefficients are sitting on. So Hn, this is a Hamiltonian, this is our Hamiltonian operator. Its eigenvalues for this state are the total energy minus the frequency on the temporal dimension of a particular wave. Okay? So we can understand this pictorially. So when applied to our Hamiltonian, we could see that these coefficients act as lowering operators on our quantum scalar field. Specifically, when applied to the Hamiltonian, we get that these coefficients lower the total energy of our field by a factor of omega, where omega, again, is the frequency of the field in the temporal direction. So we can imagine waves adding up to give us a complex-looking wave. Each one of them has a frequency in the temporal direction, where we have omega 1 for this wave, omega 2 for this wave, omega n for this wave, where n can get arbitrarily high. When we apply a, n, k, we're taking the wave of spatial frequency k, okay, and we take that out, right? Because we're taking out the energy we're taking out by a factor of omega. So we can take it out by a factor of omega n here. So this is akin to raising and lowering the total energy of our of our wave, of our quantum fuzzy wave, by a factor of omega n, which is, or by a factor of some frequency. Okay, so these things can be thought of as literally raising and lowering the total energy by reaching into the frequency bin and pulling those frequencies out, specifically looking at the temporal frequency, not the spatial frequencies. Okay? So we can do the same calculation with the complex conjugated coefficient. So with a dagger, you could pause the video. You can go through all of this. I think a lot of this is pretty self-explanatory, but we end up getting the opposite effect for this guy here, which is E plus omega. So the total picture then is that we have dagger will add Wn and not dagger will subtract. Okay, so dagger is going to add that Wn, and then not dagger is going to subtract, which is why I really like the dagger notation, because the dagger looks like a plus sign. All right. We want to again also note that the coefficients are functions of frequencies along each orthogonal axis, and so our creation and annihilation operators are really this. So when we see something like this, we should be really thinking that this is a frequency in three-dimensional space. Okay. With this in mind, we want to understand the canonical momentum of our quantum field, which will be the focus of the next video. So to get to the punchline first, what we want to derive now is this guy right here and this guy right here, where a dagger A is going to give us the number of particles in our volume. Okay, that's going to be called the number operator. We'll focus a little bit less on this, but we're going to derive this thing in the next video, and then we'll make sense of how these ends work also, either in the next video or in the video after that. But at the end of each video, we're also going to cover a flowchart of our progress to understand where we're going, and so that we can understand quantum field theory from a bird's eye view. So what we have so far, again, from quantum mechanics, apply Heisenberg uncertainty principle, we get quantum field theory, Heisenberg uncertainty principles, and then now we have quantized energies, okay, from these guys. All we really did, again, was we used these guys to get to here, okay? All right, so with that being said, I will see you guys in the next video. Make sure to hit that like and subscribe button, and yeah, I'll see you guys in the next video.